last lecture we talked about solid ignition, and one of the points made is that solid ignition is a necessary part of the physics in terms of overall descriptions for flame spread. The flame spread is this continuous ignition process for solid or condensed phase materials. And so before we talk about the theory, I'd like you to take a look at some lab demonstrations that were conducted by actually the author of the book, Jim Quinteri, at the University of Maryland. So I'm going to switch over to the PC, and again we're going to look at some YouTube videos where we can get a sense of what the issues are in flame spread. So I'm switching us over right now. And so this is Jim Quinteri, Dr. Quinteri. He's a professor, emeritus professor now at University of Maryland, College Park, and conducting this flame spread lab. And I'm going to so this is the apparatus. It's just a thin sheet of paper held fixed between these two sort of supporting rods or elements, and we're going to see what happens when this is ignited in several different configurations. So it's going to be ignited from a top configuration. We'll see burning down, we'll see burning across, and we'll see burning up. So before going into that, imagine that you're igniting a sheet of paper, so this is going to be a thin ignition problem. You do a thin ignition problem across the edge of a sheet of paper, and you compare that with this ignition where you do ignite it at the bottom. Before he does this demo, what would you expect to occur in terms of the spread rate? That is, what would you expect in terms of the rate at which the fire consumes this piece of paper? Would you expect it to be faster from the bottom or faster from the top? And why? Okay, so you have an idea about that, and most of you probably are saying that it's going to be faster from the bottom. The reason it's faster from the bottom, I imagine you're thinking, is because the hot gases are buoyantly convected upwards and allow additional preheating of the sample. So you get more and more heating of the sample. If it's just a ignition time problem, as you preheat the sample, it goes closer and closer to the ignition temperature. Obviously, once it reaches the ignition temperature, the volatiles are released and it's assumed that it can burn. The initial flame is the pilot, and so you get a rapid consumption process in this buoyantly driven case. Now, if the piece of paper had been horizontal and there's a wind blowing over it, in some respects that does the exact same thing as the buoyant convection that preheats in the gravity sort of aided case. And both of those are oftentimes called either wind-aided or concurrent flame spread. So we'll see that wind-aided or concurrent flame spread, where the flow is supporting and helping in the flame spread process. The opposed flow case, where we ignite at the top, just as buoyancy and buoyant effects helped in the downward ignition process, when it's ignited at the top, they inhibit the transfer and the burning process downwards because the flow is primarily in this direction. There's much less heat transfer that's available to heat up this fuel element, and it's a much slower process. In fact, it can actually self-extinguish. And so we know that, when holding a match, for example, that there are many times that you can't get that flame to propagate down. You turn it the other way, of course, it burns your fingers. So let's take a look at some of these issues here. Okay, so we're going to, let's see. All right, Dr. Quinteri, ignite it. There we go. So he's ignited at the top. Let's see what he has to say about this. It's spreading, but spreading quick.
You certainly see the black spot. You don't see,
Oops.
if there's a light switch someplace, somebody with the lights. So you may need to,
So we see the slow spread process downwards.
to do this. We'll have to do this with some, now you also see this physical effect that we really don't want to have in the process. So you may want to.
So I'm going to stop it for a second. You see this blue highlighted? Now, one of the things is we've talked about the fact that when you see an orange glow, that orange glow represents a lot of production of soot particles. And so we see that there's an absence of soot particles actually in this downward burning system. And that absence of soot particles is also representative of a relatively well-mixed combustion system. So the absence of soot particles here suggests that at this interface it's well mixed. Well, it's not surprising it's well mixed because, remember, we have an upward flow of air because of the buoyancy. The buoyant products are going up. Something's got to fill it in. It's the air, the cool air is mixing in from the bottom. That cool air is mixing with the pyrolysis gases, and those are burning. And then we have this almost, but it's not really quite, partially premixed or premixed type flame that anchors another flame above it, which is this diffusion flame, this non-premixed flame.
Push it away. And certainly that's measurable. Now, if we do this.
Now watch this. Look at the relative rate of burning from the bottom as compared to the top.
There is a black spot.
Let's just go back a second here. So, first of all, look at how much radiation from the soot particles is available because of the incomplete combustion to burn that in a much faster sense, at a much faster rate, and provide much more heat flux to the sample such that we do get this fast flame spread rate. Okay, so can we describe that process quantitatively? Absolutely. And we already have most of the tools to be able to do that because of what we did with the solid ignition problems. So we already said pieces of this. We said upward flame spread is also sometimes called wind-aided flame spread. It's also sometimes called concurrent flow flame spread. And the upward flow is faster than downward spread because the flame heats up the fuel surface area over a larger area. And flame spread is this is the mechanism by which an initial ignition point or source is transferred over a fuel package. So a sofa that has a cigarette or a match that ignites a small part of that sofa, eventually it consumes the whole sofa or fuel package and then becomes a compartment fire, sometimes called a room and contents fire. But this thing starts off initially as a relatively small flame that continues to grow. It wants to grow, and it's looking for a fuel as long as there's enough oxygen available to continue to grow and to spread. And from a safety perspective, garment, obviously, so there's fire testing of garments to make sure there's no flame spread or that we can inhibit flame spread using different means. Consumer products are typically there are attempts to make them flame retardant because ignition sources are ubiquitous, whether it's in electronic shorts within electronic systems. And so there are lots of different strategies that are used to try to limit the flame spread rate such that perhaps some sort of fire detector can go off before the fire grows too large. So we've said this. I'm just going to, again, highlight it. Flame spread is this continuous ignition process, and it takes place as a diffusion flame spreads over a solid or liquid fuel surface. This is the opposed flow flame spread. This is when this was ignited at the top of the fuel packet as compared to a bottom ignition process, which is called wind-aided. Now, what we're going to talk about is the fact that the velocity for flame spread can be thought of as the heated length divided by the time to ignition. And so from a matrix, you can think about, so remember, we talked about thick and thin ignition models. And now we add on top of that the possibility of wind-aided or opposed flame spread. So you're going to see that at the end of this, we're going to have this, these quadrants, and we're going to define what this flame spread velocity is for these different types of samples. So I mentioned this already, but you can have, again, on different types of elements, whether it's furniture or otherwise, we could have horizontal flame spread, laminar flame spread, turbulent flame spread, and for the opposed case, it is a slow process. And so this is opposed, and just like in opposed where it's laminar or turbulent, clearly we have the same issues here. We could have laminar or turbulent, etc. And so the flow characteristics also impact this spread process. We said it's a continuous ignition process, and what I'm trying to show here is that, so I'll actually talk about this in a couple different ways. So I call this an opposed flame spread because from an analysis perspective, I'm interested in what's happening in this sample. So this is a thin sample where in a frame of reference where the flame is fixed, we can imagine what we're doing is we're translating the solid into a region where heating is taking place. So that's what this is depicting here. Now, I'm going to switch this around also, because imagine now that on this side that this was also virgin. So imagine that this is an initial ignition process. So I have a laser source up here that I'm heating up a sample of this solid material, and there is a flow in this direction. So what's going to happen is I'm going to get, once this ignites, I'm going to get this flame that's going to lean like this. Now, the flame is going to want to propagate in both directions. Of course, it's going to propagate a lot faster in this direction than it is in the opposed direction. So in some sense, well, there's a wind-aided direction, and then there's an opposed direction. So this is what happens if you have an ignition, sort of a central ignition process with a prevailing flow direction. Now, when we talk about the flame spread velocity, what we're really talking about is the velocity of the pyrolysis front. So there's this interface where we consider that the volatiles are coming out of the solid, and the extent of that is really what we're interested in. So I can think about this perhaps as XP in maybe this positive direction, and XP in the negative direction. And what we're looking at is dXP dt when we're talking about this flame spread rate, where dXP in the positive sense in the wind-aided direction is faster than in the opposed direction. We'll see this in some other schematics, but the issue is that the heat flux from the flame is going to heat up this material, and as it heats this material up, so there's an influence region, there's a flame length over which this material is heated. As it's heated, there's a time for ignition associated with that heating, and we can write a simple differential equation for the velocity because of that. Now, the flame spread rate should not be confused with the flame speed. Remember, we talked about laminar flame speed. In fact, there's a good point to be made here too. So there's a laminar flame speed, remember we said was the speed at which the premixed flame front overtakes the reactants. Well, now, this is in some sense the limiting velocity that you're going to have in a flame spread problem. Because if, for example, there's this huge heater that's heating up stuff even further than where the flame was heating stuff up, you can imagine that you can bring up the surface temperature of this condensed phase of this solid material to the ignition temperature, at which point it's liberating pyrolysis gases like crazy. These pyrolysis gases are mixing with the air because of buoyant effects, and so you have basically a pre-mixed flame well ahead of wherever you've ignited it, and so you get this rapid propagation where the rapid propagation might be at some premixed flame speed, and it could be a laminar premixed flame speed, it could be a turbulent premixed flame speed, depending on the external flow conditions. But this, in some sense, then represents an upper limit to what you might be able to get for propagation as compared to the flame spread rate, which is a different issue. Okay, so in this wind-aided spread, again, flame spread in the same direction as the wind, the flame is heating up this sample. So we might have imagined that we ignited the flame back here, and there's a burned out region where it's just charred. There's a length associated with pyrolysis, this x sub p, and there is a heating length, which is called delta here. And the delta can be quite large in the wind-aided, which is very different from the case for opposed, where it's relatively small. And it really has to do with how large the flame is. Now, a lot of times we model the flame heat flux as being somewhere in the range of 20 to 30 kilowatts per meter squared. So you'll see a lot of cases where I'll just approximate this as 25 kilowatt per meter squared, and this is consistent with what we'll see in the textbook. The types of problems that we're interested in solving with this, there are a whole range of interesting problems, but primarily we're asking ourselves, what is the flame spread velocity as a function of time? And you'll see in subsequent discussions that, again, we say that this is some heating length divided by the ignition time, and we say that that heating length can be written in many cases as a flame length minus the pyrolysis. So now I'm going to do it a little bit differently. I'm going to look at it as a pyrolysis length, sort of from an actual origin divided by this ignition time. Now, this becomes a differential equation because I mentioned earlier that the flame spread rate is really the way we talk about it is the change of the pyrolysis length with respect to time, and we see that that's functionally dependent on the pyrolysis rate. So we see that this problem is we have to solve a differential equation to figure out how this evolves. All right, so for a thin concurrent or wind-aided problem, we already know what the ignition time is. And so the ignition time, as you recall, for a thin problem, so if you look at our so remember, it's rho c d, we called it d earlier, T ignition minus T0 over the heat flux. So here we have the ignition time, and here we have the heating length. Now, we haven't specified what that heating length is yet, but as far as just the general discussion, we understand that this makes sense. And again, here we have the change in pyrolysis length with respect to time. For the thick case, it's the same overall energy balance, so this is just a convective energy balance, except that, and this is a little sort of odd here. So this isn't, this, okay, so I'm okay, good, this is right. So good. So the characteristic time is still delta over V, but in this case, our heat flux, remember, or our ignition time looks like K rho C T ignition minus T0 T surface squared divided by Q squared. Okay, so this is again from our last lecture. And remember, we had a pi over 4 there, so this is from scaling again. Okay, so what we haven't defined is delta. What is delta? Okay, and we need to figure out what that is. And so let's do it with a real problem. And so actually, before we talk about the real problem, let me just go over again sort of the physics of the problem here. So in this wind-dated flame spread problem, so we ignite it at some initial location. There's a pyrolysis length, there's a heating length, there's a flame length. And so in the pyrolysis zone, so let me write this down. In the pyrolysis zone, there is mass flux, there's volatile flux. This is where the fuel vapor, so this is fuel mass flux. And that fuel is just the pyrolysis gases from the solid decomposition. So this stuff comes out of the material. It supports this diffusion flame. Remember, the diffusion flame is an interface between fuel and oxidant on the outside, so it supports this diffusion flame. That diffusion flame heats up, it's leaning because there's a flow in this direction. There's a V, or U infinity or V infinity, a gas flow. It heats up this virgin material and heats it up to the ignition temperature. And as we said, the flame spread rate is just the rate of change of the pyrolysis distance with respect to time. And we said that that heating length, as you can see graphically here, is really the flame length minus the pyrolysis length. And again, so burnout obviously occurs. I mean, you know, if it's a thick enough sample, if it's a sample with some sort of ash content, you're not going to be able to burn all this fuel. All this fuel does not get converted into pyrolysis gases. So in the idealized case, you know, that we'll see in one of the examples, there is no burnout. So I'm going to look at an example in Quintili's book where he says, you have a sample of, there's a wall where it's, you know, made out of some flammable material. So here's the floor. Somebody puts a pan of gasoline that they light, so maybe an arson case, and this initial flame from the gasoline is going to set up an ignition. So there's going to be an initial ignition distance, and that's going to be our initial pyrolysis length. Once it's ignited, both the gasoline and the mass flux of volatiles from the wall are going to support a much larger flame, and that larger flame is going to heat up the wall and cause a flame spread over the wall over the LF length scale. And so as this pyrolysis front moves, the flame length is also going to increase because more gas is coming out of the pyrolyzed region, and it burns faster and faster. Now, in reality, we understand that there is burnout, that at some point you deplete the burning sample of pyrolysis gases, and so what one must really do is one should track the burnout zone, and I'll show you how to do that in a little later section. So we should be really tracking the burnout distance as well as the pyrolysis distance as well as the flame length. Okay? So an example here. A 1 meter high slab of polymethyl methacrylate is ignited at the bottom and spreads upward. Ignition is applied over a length of 5 centimeters. Okay, so just maybe make this a little bit bigger. So in a 5 centimeter region, we have ignition. Once we have ignition, the assumption is that we have a mass flux of the methacrylate, the methyl methacrylate, this fuel, out of the region that has been ignited. The slab is 1 millimeter thick, ignited on both sides, so we can think about some axis of symmetry. How long will it take to be fully involved? So it's 1 meter high, and the question can be interpreted as how long is it going to take? Polymethyl methacrylate actually melts and drips, but let's forget about that right now. But the question may be, how long does it take before X of P, so this pyrolysis length, which started off at 5 centimeters, how long does it take before X of P is equal to 1 meter? So that's one interpretation. Another interpretation could be, how long does it take for the flame to actually touch that 1 meter point? And, you know, they're not very different in terms, I mean, the analysis is exactly the same. It's just which of these variables do you want to process it based upon. Okay. So one of the things is that, let me erase this here. Well, here I have it as YP, but it's, you know, I have it as XP here. I'm going to make this XP. So at what time is XP equal to this height? And so the heat flux from the flame, we said, is 25 kilowatt per meter squared. The mass of volatiles out of the wall is going to be related to the heat flux divided by something you might consider like a latent heat of vaporization. And it's not right strictly, but it's a simple way of modeling the energy required to liberate the volatiles. And so there are correlations like this, and you'll see this in quinteria, that says that the flame length is proportional to the heat release rate, for example, per unit width. So what this requires us to do is to model this heat release rate. So HRR is heat release rate. So the bottom line is, and the prime here is per unit width. Is that once we model XF, we'll find out that XF is actually equal to some constant times XP, and so this whole thing can be thought of as K minus 1 times XP divided by T ignition. So it's a first order system in XP. We'll see that it's an exponential dependence. So XF 0.01 Q dot prime. Again, QF is 25 kilowatt per meter squared, a latent heat of vaporization, such that we can identify, and again, we know T ignition. We're going to model it as a thin ignition process. And to find XF, we need to find Q dot prime. So to get Q dot prime, if you have a mass flux of volatiles coming out of a wall or out of any material, the assumption is that all this stuff is burning in the flame, in some sense, instantaneously. So in sort of like in a steady state, the mass flux of volatiles times the heat of combustion is equal to the overall heat release rate. So let's write that. Q dot is equal to m dot fuel times delta HC. We've talked about these different things before. Again, this is the mass transfer rate of fuel, mass flow rate of fuel. Let's make it easier on ourselves. Fuel mass flow rate. Delta HC, of course, is our heat of combustion on a fuel basis. And so for some of the types of pyrolysis gases that you liberate for solid combustion, we have things like 24 kilojoule per gram for the heat of combustion. So like cellulosic materials and a lot of polymers. Cellulosic materials are actually closer to like 16 to 18. So cellulose is like 16 kilojoule per gram, but a lot of polymeric materials, off-gas things, where they're closer to this 24 kilojoule per gram. Remember, if we had, my favorite gases, things like methane, propane, etc., these things are more like 44 kilojoule per gram. There are a lot more oxygenates and a lot more other stuff that comes out of these materials, and that's why you have a lower heat of combustion. Okay, so the pyrolysis area is just the pyrolysis length times a width. So on a width basis, we see that there's this proportionality to the pyrolysis length. And so this law of XF, or some sort of this empirical relationship of flame length dependence, on heat release rate per unit width translates into the flame length, XF, not XP, XF, flame length, translates into XF being, again, proportional to XP. So, I already mentioned this, that now the differential equation looks like dxp dt is equal to k minus 1 xp over T ignition. First order ODE, we integrate it, we get an exponential dependence. Okay, so that's quite simple. It says that in 17 seconds we invert it. And the inversion says that T is equal to T ignition over K minus 1 ln XP, sort of a T final, which we know, over XP0, where this is the 1 meter, and this was our, what did we say, 5 centimeter. Okay, so we say in 17 seconds this thing will fully engulf it. Now, PMMA doesn't have burnout, so this is a reasonable approximation in some sense, although PMMA melts and drips, so there are different aspects of this. For a problem where there is burnout, so for materials that perhaps char, and where the char protects the virgin material underneath, there's a limited amount of pyrolysis gases that are going to evolve from this system before it basically shuts off and says, hey, no more pyrolysis gases. So in this case, again, if we are referencing everything to sort of zero length, then you see what's interesting about this is that the region over which the gases evolve is no longer proportional to xp, it's proportional to xp minus xb. Okay, so so the mass evolves from xp, xp minus xb. Okay, and so now there's some rule or law that's going to tell us how xb evolves, and that's a burnout time basically. The flame length is going to be cast not in xf but in xf minus xb. Okay, so we're going to recast it in xf minus xb, and so our original law is which is still true. It's dx pdt is equal to xf minus xp over T ignition. Again, that's our heating process over here. But we're going to cast xf minus xb in terms of, and we're going to, this is really messy what I wrote here, but we can rewrite it as this xf minus xb and xp minus xb over T ignition. So let me make it a little bit clearer, okay? So I think we did actually. So xf minus xb so the flame length is still proportional to the heat release rate per unit width. This heat release rate is, again, m dot times our area times our heat of combustion. The area, in this case, is equal to our width times xp minus xb. So we have xf, which is referenced, okay, so this is the key point. So xf is the flame length, but it's the flame length referenced to 0. So that's why we have to say xf minus xb, because this is in some sense, this is the, you might want to call this the flame length. xf star is the flame length reference to the base of the pyrolysis zone. And so xf minus xb is this, there we go, is this xf star. So xf minus xb is equal to some constant times xp minus xb, and that comes from this per unit width issue. So, so when we have, and you'll follow it here because it's correct, but it's just a little bit more confusing. So when we write this xf minus xp, all we're doing is we're subtracting off xf minus xb and xp minus xb. We're basically subtracting off so we have xf minus xb plus over T ignition minus xp minus xb over T ignition. Okay? So this is equal to this minus that, xf minus xb over, and okay, perfect. And as we said, xf minus xb is just constant xp minus xb. So we get this is equal to constant times, okay, and I'm just going to, sort of combine these two, and so it's equal to constant minus 1 xp minus xb over T ignition. So we basically can write dxp dt as constant minus 1 xp minus xb over T ignition. But the problem is that we need to solve a coupled equation for xb, and that coupled equation from xb comes from here. So, and so this what I wrote here is exactly the same as what I have written here, except I think hopefully I showed it a little bit clearer here. To actually solve this, one convenient way to do it is to subtract off the xb equation, the burnout zone equation. So we have one variable, which is just xp minus xb. You can call it phi, you can call it whatever you want. And so we get a differential equation in terms of xp minus xb, and we see that it's dependent on the ignition time and the burnout time. If, for example, the burnout time is very, very fast, we see that this thing extinguishes, because if the burnout time is a small parameter, this whole thing is driven by the burnout time and is all negative. And so xp minus xb is a decreasing function of time. Basically means that the burnout zone catches up with the pyrolysis zone. Similarly, if it's a very long burnout time, then we get the acceleration that we saw earlier for the simple no burnout case. And I'll summarize that at the end. Opposed flame spread is a harder problem than the wind-aided flame spread problem. And the reason it's harder is because it's harder to define the length of the physics of heating. I mean, it's not hard. It's hard to sort of, from first principles, really, perhaps, to define it. And one simple way that it's defined is this. The simple model is that at this edge, you remember that there's a sort of a quenching zone, that the region where the flame sits off of the wall is approximately the same region over which there's heating of the solid. So the model, in some sense, says that this sort of quench distance is comparable to this heating distance. And so if you remember from some of the earlier discussions that we had, we said that this is basically a convection diffusion balance, and that there's a characteristic length scale associated with that, where the characteristic length scale looks like the velocity divided by the, it looks like the thermal diffusivity divided by the velocity. And so that's what we're going to see in a second here. So overall energy balance is always the same. We're translating material in, and it's getting heated up over a distance delta. But that delta distance is this preheat length scale, and that preheat length scale comes from this convection diffusion balance, and as we said, is alpha over a velocity. I'm going to call it Vg. So the preheat length scale looks like delta, which is alpha over Vg. Let's just make sure from a units perspective this makes sense. Meters per second, meters squared per second divided by meters per second. And the convection diffusion balance that tells us how large that zone is given as follows. And, you know, I did a lot of different things here, and so let me just walk you through it. So this velocity is the flame spread velocity. This is the gas velocity, and what I'm saying here is that the again, this is a convection. This is an approximation for this heat transfer rate, and again, it's over the same preheat. This is the model I was showing you earlier, So this is delta, and that delta is assumed to be the same as this delta. Sort of more intuitive, or certainly I think clearer, is this interpretation that we're heating up the gas that's coming into the flame by conduction, but it's opposing the diffusion. And so if this gas layer is has sort of like the same length scale as the heating process that's happening here, that's the justification why delta is the same on both sides. And from that perspective, there's sort of another convection diffusion problem that we should look at. I mean, here it seems like it overall balances out. But the other convection diffusion problem that we should be looking at is the gas phase conduction diffusion analysis. And that gas phase convection diffusion analysis says that rho CVG, again, some delta T over delta looks like Kg delta T over delta squared. And this is where I got delta looks like Kg over rho C Vg. And this is our alpha over Vg expression. So we know delta looks like alpha over Vg. In some respects, this isn't asking for us to know that, but we do know that. We know what this delta looks like, which is shown here. By this approximation that they're equivalent, we lose that, and we get sort of a funny Kg over, because this is K gas over rho C of the solid. So these are solid properties on the denominator, but a gas property in the numerator. It's essentially the same analysis from the perspective of delta of delta for the preheat length. So again, the approximation is that even if it's a thick material, it's exactly the same idea from that perspective. The difference, of course, is that our ignition time is different, and this is, we know that from our previous work. So this the dependence on this guy is different, and it still looks like our ignition time problem. So that's not different. Okay, I'm going to summarize this by saying that we know what ignition, we're going to use the short time ignition models, so no convective losses. And this is from the last lecture. We know what T ignition is in short time for a thick sample and a thin sample. For the wind-aided problem, so all these problems now in this quadrant here, all we're doing is we're saying that VP is, again, LF over T ignition. So VP for these problems is, for the thick case, looks like Q squared, the heating length, divided by our K rho C, T ignition minus TS squared. For the thin case, very similar description for the wind-aided. For the opposed, there is a question that remains about, again, this value of delta sub F. So, here we sort of sweep it under the rug by saying that we can define a delta sub F in terms of these gas and solid parameters. But in reality, and so this is the issue, in reality, we really don't know what a good way of defining this heating length is. So the heating length is somewhat is dependent on the analysis you use in some sense. Is most uncertain. And so what happens is that tests are used to parameterize it. Or perhaps to say to calibrate it out. And the experimental condition is this lateral ignition flame spread test, this lift test. And so there's a parameter in this lift test that looks like Q squared delta F. And so a lot of times for opposed flow flame spread, it's this, these tabulated parameters are used to specify the flame spread velocity. Okay, I think we're going to do smoldering next lecture, so we will call it quits for this lecture. All right, thanks for your attention.